Hi everyone. This is our look at bond polarity. This is a new topic for us and it stands apart a little bit from our work on stereochemistry and other kinds of diagrams. It's based on this concept of electronegativity. Electronegativity, it's an expression of an atom's affinity for electrons. Let's focus on that word affinity for a second. We use it in our regular lives sometimes for a person who picks something up quickly. Imagine if a person was 20 years old, they had never taken piano lessons before, and they start taking piano lessons, and all of a sudden, really quickly, they just pick it up so fast, and they're amazing. We would say, oh, that person had an affinity for playing the piano. They picked it up really fast. So it's not quite perfect, but it's good enough for now to say that electronegativity, it talks about, or it shows an atom's ability to pick up electrons, how badly an atom wants to gain electrons. We can find it on the periodic table. It's right in each individual element's box. For example, fluorine is 4.0. It's the most electronegative of them all. The highest number for electronegativity on the periodic table, the most electronegative, is fluorine, and it only has 4.0. This value does not have units. Hydrogen, if we look it up on the periodic table, it has an electronegativity of 2.2. When we have two atoms bonded together, because this is bond polarity, if we calculate the difference, if we just do some subtraction, the difference between electronegativities is going to allow us to classify the bond. This introduces a third category of bond for us. If the difference, if after we do the subtraction, is greater than or equal to 1.7, then we're going to have an ionic bond. This means that one element really wants the electrons really badly, it's really strong, and the other element does not. So the strong one takes that electron and keeps it. And the other atom has lost those electrons permanently. This is not sharing. This is taking and losing. It's bullying. It's not sharing. If we have a difference of less than 1.7, so 1.6 or smaller, then we have a polar covalent bond. It means we have sharing, but that sharing is unequal. One of the elements is keeping the electrons more than the other. Yes, they are sharing. They're passing that pair of electrons back and forth. There is sharing, but one of them is unequally hogging a bit of the electrons. The other one is a little bit different. We need to explore that a little bit more in a minute. If there is no difference between the two electronegativities, there is no difference if both of them are equally strong, if they have an equal affinity for electrons, if they have an equal electronegativity, there is no difference. We have a non-polar covalent bond. We have equal sharing, fair sharing, totally equal. They're all the same strength, equal sharing of electrons. Here's a more detailed look at the polar covalent situation, which is our most common situation by far. Here I have a really simple molecule, HCl. I've already gone and looked up the electronegativities. When I look up hydrogen on the periodic table, its electronegativity is 2.2. When I go to the periodic table and look up chlorine, there the electronegativity is 3.2. So what's the difference between 3.2 and 2.2? 1. The difference is 1. 1's not 0, and 1 is less than 1.7. So we're in this polar covalent situation. So looking at these numbers, which element wants the electrons more? The one with the higher electronegativity. Chlorine is going to be keeping the electrons more often than the hydrogen. Let's say that in a different way. The pair of electrons in the covalent bond are going to spend more of their time around the chlorine atom than the hydrogen atom. Not all of the time, just more of the time around the chlorine and less of the time around the hydrogen. We have unequal sharing. The element with the higher electronegativity is going to keep the electrons more than the other one. Because of this, we have some new notation to say. Okay? The larger electronegative element is partially negative. Electrons are negatively charged, and the chlorine is keeping them more of the time. It doesn't always have them, so it doesn't take on a true negative charge. It didn't take the electrons and keep them. It's passing them back to the hydrogen sometimes. So it's only partially negative, or mostly negative. And we have a special symbol for showing that. It's a curvy D. It almost is like a D turned into an S. This is a lowercase Greek letter delta. In science, it always means partial. Lowercase delta is partial, and it's negative. The larger electronegative, the element with the higher number, is going to take on this partial negative charge. Start to make an S and turn it into a D, a lowercase Greek delta with a negative. And then the other one, the lower electronegative element is partially positive. The hydrogen here has lost its electrons for most of the time. Not all the time. It's not taking on a true positive charge. It's taking on a partial positive charge. Here, I'm starting to make an S, but I turn it into a D, and it's positive. One other thing, we're going to draw an arrow pointing at the more electronegative element. Where are the electrons going? Chlorine here is keeping them. So, when we are in the polar covalent category, when the difference between the two elements is greater than 0, but less than 1.7, we're talking about unequal sharing, a polar covalent bond. The element with the higher electronegativity takes on the partial negative charge. We have this strange symbol, lowercase Greek delta, which means partial negative. The smaller electronegativity, the one that's getting the short end of the sharing, gets a partial positive charge. And we also include this arrow in order to show where the electrons are spending most of their time. The larger number is hogging them. Electrons themselves are negative, so we have the partial negative charge there. This is kind of a random number, 1.7. If the difference is big, there's a really strong one and a really low one. The stronger one just takes it, and we have a transfer of electrons and an ionic bond. Most of our times that we're dealing with these kinds of things are polar covalent. If it's the same atom, two N's, two O's attached to each other, then we're going to see non-polar covalent bonds, equal sharing if there is no difference. We have some new notation. This Greek letter delta, lowercase delta, is something that we maybe have not seen before. We're going to use it in all kinds of situations moving forward in your life, not in this course, to mean partial. The higher number, partially negative, the lower number, partially positive, and put an arrow pointing at the higher number. And I hope that helps.